Welcome to Hench Maths. In today's video we're going to be working through integration by parts. Now this is an integration technique which is in the second year of your A-level course. It's a lovely method and I think once we work through it you'll see that it'll be one of your favourites too. We're going to do the proof, so we're going to derive where it comes from using the product rule, and then we're going to work through 8 examples. Now these examples will get steadily more difficult, ending with a couple of spicy ones at the end, so questions 7 and 8, a bit of fun. As always, when we work through these questions, once you feel confident, pause the video, work it through yourself, and see if you can do it independently. That will always be more valuable to you. Okay, so let's prove where the formula comes from to begin. So the proof of the integration by parts formula comes from the product rule. And so let's do a little reminder of that. So the product rule is a differentiation technique for when you've got two functions multiplied together. So here we've got the derivative of uv is equal to u multiplied by the derivative of v plus v multiplied by the derivative of u. It's a nice one to do. So let's do a little example. So if we had differentiate y equals x squared times e to the power of 3x. So the way I'd like to lay it out is label our functions. So if I said u is equal to x squared and v is equal to e to the power of 3x, then we make a little grid. If I then find the derivative of this one, so u dash would be 2x, and v dash using the chain rule, we'd end up with 3 e to the power of 3x. Once we lay it out like this, it's nice and easy to differentiate it. So what we do is we just cross multiply like this. So we end up with x squared times 3 e to the power of 3x, which gives us 3x squared e to the power of 3x, plus 2x multiplied by e to the power of 3x. You can actually factorize that, which is it's a nice thing to do, because maybe if you're trying to find a station rule a bit later on, so we can take out an x, we can actually take out an e to the power of 3x, and in your brackets you'd have 3x plus 2. So that's an example of the product rule from differentiation, again part of your second year of your A-level course. So to prove the integration by parts formula, what we can do is simply integrate the product rule formula. So I'm just going to add an integral symbol here, integral symbol here, integral symbol here. So imagine we're integrating this side, so if we integrate these, and we can do those separately because it's the addition of those functions. Now the nice thing here is that if you integrate the derivative of a function, you get back to the original function. So the integral of the derivative of uv is simply uv. So we end up with this. And then we are only one step away from our integration by parts formula. If we make u derivative of v the subject, we get uv, and we just need to subtract this over to the other side, so subtract v u dash, and that is this famous formula. It's in your formula book. It's the integration by parts formula. Now let's apply it. It always makes so much more sense once you apply it to a question. Okay, so let's apply our integration by parts technique to this example here. So this is a nice first example. We've got some nice simple functions. So what we're going to do is firstly just remind ourselves of the formula. So it tells us that the integral of uv dash is equal to uv minus the integral of vu dash. Now if you look to this function we're integrating, we've got x multiplied by e to the power of x. So we're going to assign one of them to be our u and one of them to be our v. Which one is the question? Now I'm going to tell you now we're going to take our x to be our u and we're going to take e to the power of x to be our v dash. Why that is will become clear as we work it through. So if you remember when we were doing product rule, what we said was, well, if we call our function, so u we know is going to be x. Now the difference here is we don't actually know what v is. We know what v dash is, which is down here. So if I say v dash is equal to e to the power of x. Now to apply the technique, we actually just need to find these missing functions. So it's a bit like product rule, except we need to work backwards to find this one. So the derivative of x, so u dash will be the differential of x, which is 1. But to find v, because we have the derivative already, we actually need to integrate e to the power of x. So the integral of e to the power of x is e to the power of x. So effectively, what we're doing here is we are differentiating down but we're integrating up to find our missing functions. Now, once you've found these functions in your grid, once you've got them all, we can now just stick them in the formula. So the integral of x multiplied by e to the power of x dx is going to be, so it's uv, so these two times together, so x e to the power of x, subtract the integral of vu dash, so these two times together, vu dash. Now 1 times e to the power of x is just e to the power of x. So this is how this formula is nice, because you ended up, because one of the functions differentiated to 1, just a constant, you've ended up with something at the end that you can actually now integrate. So the final answer is going to be x e to the power of x subtract the integral of e to the power of x, which is just e to the power of x, and then we add in our constant of integration. And there you go. That is the first example of using integration by parts. So effectively what we did here is we assigned one thing to be our u, the other to be v dash, so it's a derivative. So then to find the things you need for a formula, we need to differentiate one, integrate the other one, and then if you use this grid method, which I do recommend, effectively you're going to get these two times together, subtract the integral of those two times together. Now, whenever you do an integral for the first time, or you've learned a new technique, you want to just check that it works. So we've got our answer now. So if we differentiate it, we should check that it gets back to the original. So what we're going to do now is just to double check, we're going to do the derivative. We're going to do the derivative of what we got. And just check that that gets us back to x e to the power of x. So we can actually do this using the product rule. So x e to the x is functions times together. So it would be x multiplied by the derivative of e to the power of x, which is that, plus e to the power of x multiplied by the derivative of x, which is just this. Then we need to integrate this part, which is just the same thing, but the negative, and the c disappears. And you can see that you get e to the power of x, subtract e to the power of x, cancels out. And so if you differentiate our answer, you get what we originally integral. So this integration by parts technique, it works. Let's do another example. Example 2. So we're going to integrate theta multiplied by cos theta with respect to theta. And we're going to use integration by parts again. So let's remind ourselves of the formula. So the integral of u v dash is equal to u v minus the integral of v u dash. So again, in this case, I'm going to assign theta to be our u and cos theta to be our derivative of v. Using this grid we used earlier, if I say that u is theta and v, the derivative of v, is cos theta. So if we differentiate theta with respect to theta, we get 1. And we just need to remember how we integrate cos theta. So the integral of cos theta is sine theta. So now we have our grid filled out. We can now, so I'm actually going to, in this one, I'm going to call this integral I. So I will be u multiplied by v, so theta sine theta, subtract the integral of v multiplied by u dash, which will just be sine theta. So the integral becomes theta sine theta minus the integral of sine theta. Now the integral of sine theta is negative cos theta plus c. So we get negative cos theta. So because it's a double negative, we're going to get plus cos theta plus c. And you can see that when we get this sort of got a theta multiplied by a function or an x multiplied by a function, often it's very useful to take that to be your u, because when you differentiate it, you end up with something that's simpler, something that's just constant, so that your final integral comes through nicely. So the integral of theta cos theta with respect to theta is theta sine theta plus cos theta plus our constant of integration. Okay, So we have the integral we did previously, but now we've added in some limits. So it's always important to remember that when we integrate, often we'll need to apply a context to that. So for example, if we're trying to find an area between the curves and the axes, we would need to do some integration with. Okay, so now we have the integral we did previously, but we've got some limits here. So it's always important to remember that sometimes when we integrate, we'll need to integrate between limits. Maybe we're trying to find some areas. So let's remind ourselves so that when we integrated, okay, so now we've got the integral that we did previously, but we've added in some limits. So it's always important to remember that when we integrate, sometimes we need to integrate between limits. Potentially we're finding the area between the curve and the axes. So if we remind ourselves, the answer we got previously to our integral was theta sine theta plus cos theta, and our limits will come to here. Now, very important fact, remember that this is all radians. Whenever you're doing calculus, you must remember we were working in radians. So let's add in our limits. So we're going to get pi over 2 for theta multiplied by sine of pi over 2 plus cos pi over 2. Now let's try and do this without a calculator. Then we're going to subtract. So this 0 multiplied by sine theta, we can see it's going to be 0 plus cos of 0. So that's a 0, not a theta. So sine of pi over 2 is 1. So we're going to get pi over 2. Cos of pi over 2 is 0. So this will become 0. 0 times sine 0, which is also 0, is going to be 0. And cos of 0 is 1. So our final answer is going to be pi over 2 minus 1. It's an exact value. Okay, example 3. So we're going to integrate a multiplied by sec squared a with respect to a. So let's again remind ourselves. So we're going to uv dash is equal to uv minus the integral of v u dash. Again, we're going to choose the variable here that's going to simplify nicely when we differentiate it. So I'm going to assign u to be a again and v dash to be sec squared. So if u was a and v dash is sec squared a, if we differentiate a with respect to a, we get 1. And we just need to remember the integral of sec squared a. So if you remember from differentiation, when you differentiate tan, we get sec squared. So when we integrate sec squared, we get tan. So we're going to get our v is going to be tan of a. So let's put them in. So I'm just label this I. So the integral is going to be uv, so a tan a, subtract the integral of vu dash, which is tan a dA. Now, how do we integrate tan a? So because tan can also be written as sine over cos, we end up with something that's in the form f dash x over f of x. It's not quite perfect, but we know that if we integrate something in this format, we're going to end up with a natural log. So tan is one of these examples where we actually go from a trig function and end up with a natural log. So the integral of tan is actually the natural log of sec a. Now I derived this in another video, so it's important that you know where that comes from. We get this. Now, if we remind ourselves of our rules of logarithms, so you can leave your answer like this. Because you've got a negative out in front, that actually means we can take that up as a power. So if we have sec a to the power of minus 1, that's just 1 over sec a. And 1 over sec leads us to cos a. So you can actually, a nice little simplification here is the integral of a sec squared a comes through to be a tan a plus the logarithm, natural logarithm of cos a plus c. So that's a nice one. I like this example because you've got lots of different things. You've got to remember how to integrate sec squared. You've got to remember how to integrate tan. You've got to remember integration by parts. It's a nice one. Okay, let's move on to example 4. So example 4 is a big one. So we're integrating the natural log of x. Now you look at that and you think, A-level maths, that is an integral I feel like we should be able to do. So how do we do it? And we use integration by parts. Now let's remind ourselves of the integration by parts formula again. So we've got u v dash equals u v minus the integral of v u dash. And you might be thinking now, okay, well, here I don't actually have 2 bits to it. It's just the natural log of x. So the trick here is to think, well, whenever you've got something that's on its own, it is technically one of those. So if we write this as lnx, the natural log of x is 1 lnx. We now give ourselves 2 parts which we can potentially use the integration by parts formula. So what we need to do is we need to decide which of these is going to be our u and which is going to be our v dash. And I'm going to tell you that we're going to take u to be the natural log and v dash to be the 1. When you do integration by parts with natural logarithms, and when you integrate with logarithms, it becomes often that you are going to need to use integration by parts. We generally, and almost always, will take our u to be the natural log. The reason being now is when we apply our formula, it was going to come through nicely. So if we say that u is the natural log of x, and in this case, the derivative of v is our 1, again, we're going to fill out this grid. So differentiate the natural log of x is 1 over x. It's an important fact we should be confident with. And if we integrate 1, we get x. So that looks a bit too much like a u. So if we put this all into our formula, so we're going to get u times v, which is going to be x multiplied by ln x, subtract the integral of vu dash, which is x multiplied by 1 over x dx. Now, that's nice because x multiplied by 1 over x, the x's cancel. So we're left with just the integral of 1, which actually we did here, didn't we? So if we then go to the final answer, we'll see that the integral of 1 is just x. So we get x ln x minus x plus c. So the integral of the natural log of x is this. So this is our result. This is a really important result. And you might think, well, that looks a bit more complicated than I might expect. You might think you might get a simple thing. If you differentiate the natural log of x, you get 1 over x. We've got this thing in parts. But let's check. It's very important that we're confident that this is how we integrate it. So if we differentiate what we got, so x ln x minus x plus c. To differentiate this, we'd need to use the product rule. So I need to do x multiplied by the derivative of ln x, which is 1 over x, plus ln x multiplied by the derivative of x, which is 1, minus the derivative of x, which is 1. Now we get the same thing again. These cancel out to be 1, which means that cancels out with that. And so we end up simply with the natural log of x. So we can see that if we differentiate x ln x minus x, we get the natural log of x, and thus if we integrate. So really important technique. Whenever we're integrating ln x, we can separate it into 2 parts, 1 multiplied by the natural log of x. We differentiate the ln x to get our u dash, and we integrate 1, and it all comes together for this result. So that's a really important one to know. Example 5. So now we're going to do the integral of x times the natural log of x with respect to x. This is a great question, and the reason is it's a bit of a mischievous one. So what are you going to choose here to be your u, and what are you going to choose here to be your v dash? I suggest that you pause the video and have a go and see how you go with it and see how you fare, because you'll learn a lot from doing this. I'm going to tell you that actually what we need to do is we need to take our u to be the natural log of x, and our v dash will be the x. So let's work it through and you'll see why that's the way round that we want to have it. So if we had u equals the natural log of x, v dash is x. If we differentiate the natural log of x, we get 1 over x. And if we integrate x, we get x squared over 2. Add 1 to the power, divide by the 2. So if we put this all into our formula, so the integral is going to become uv, so the top two multiplied together, so you're going to get x squared over 2 multiplied by the natural log of x, subtract the integral of v u dash, so x squared over 2 multiplied by 1 over x. And you can see that the x's are actually going to cancel. You're going to end up with x over 2. So we get minus the integral of half x, which we can do. Well, we've already integrated x once, so we're just going to do a very similar technique. Integrate x over 2, so add 1 to the power, so we get x squared, divide by 2, so you're going to end up with x squared over 4 plus c. So this is a really nice one. You can see by choosing your u to be the natural log of x, it actually cancelled out the 1 over x with the x squared, and it all comes through very nicely. I actually created a meme for this. It's one of the nerdiest things I could say, but this is what happens if you choose wrong. If you end up taking your u to be the x, you'll end up, your integral goes a bit round in circles. Okay. So that's the integral of x multiplied by the natural log of x. Example 6, we have the integral of the square root of y multiplied by the natural log of 3y with respect to y. So in this case, what we're going to do is we're going to choose our u to be our natural log, and we're going to choose our v to be the square root of y. So u, so our v dash is going to be the square root of y, and u is going to be the natural log of 3y. So we put these all together. So u is going to be the natural log of 3y, and v dash is going to be the square root of y, which is y to the power of half. When you differentiate the natural log of 3y, you just get 1 over y. There's a couple of reasons for that. So reason one is I could say, well, ln of 3y, using the rules of logarithms, is the natural log of 3 plus the natural log of y. When you then differentiate that, then effectively the ln3 is a constant, so it disappears. So it's the differential of lny, which is just 1 over y. You could also use the idea that it's the derivative over the original. So when you've got ln of a function, if you differentiate that, you get the derivative over the original. So in this case, we would have 3 over 3y, which just cancels out to 1 over y. Quite a detailed explanation of that, and I've got a video on logarithms that explains all of that. Integrate y to the power of half, so we add 1 to the power, and we get y to the power of 3 over 2. Divide by 3 over 2 is the same as multiplication by 2/3. We get 2/3 y to the power of 3 over 2. And there you've got your components to put them into the integration by parts formula. If I call the integral I, so we're going to get uv, so 2/3 y to the power of 3 over 2 multiplied by the natural log of 3y minus the integral of 2/3 y to the power of 3 over 2 multiplied by 1 over y dy. So I squeeze that in that gap there. Right. So the trick is, because we're dividing by y, that's just going to subtract 1 from the power. I'm just going to rewrite that integral a bit neater. So And you can take constants if they're multiplied outside the integral, so I sometimes like to do that. So I'm going to take the 2/3 out in this case, and it's just going to be y to the power of a half dy. So we've already integrated y to the power of a half. We know it becomes 2/3 y to the power of 3/2. So bringing it all together, we're going to get 2/3 multiplied by 2/3, which will give us 4/9. That's not a 9, that looks like a G. So 4/9 y to the power of 3/2 plus c. And that is how you integrate the square root of y times the natural log of 3y. We get 2/3 y to the power of 3/2 multiplied by the natural log of 3y minus 4/9 of y to the power of 3/2. So a bit of a mouthful, but that's a nice integration by parts question. And again, we had a natural log in there, so we took that to be our u, as has been the case in lots of other examples. Example 7, the integral of x squared multiplied by sine 2x with respect to x. Now this is a spicy question. We've got a green pepper in the corner, but it's actually not too spicy really, so that pepper's more of a Padron pepper. It's still a tasty question though. So what we're going to do is we're going to use the formulae uv. Okay, so what we got? Example 7, the integral of x squared multiplied by sine 2x. So this is one of our first spicy questions. We've got a little green pepper in the corner. It's not actually too bad, so it's more of a Padron pepper. So it is tasty though. So we're going to be using our classic integration by parts formula. uv dash integrates to uv minus the integral of v u dash. Now you notice the difference here is we've actually got x squared. But we're still going to take that to be our u, and we're going to take the sine 2x to be our v dash. So if we lay that out as we have been doing, we're going to get u equals x squared, and v dash is going to be equal to sine 2x. Differentiate x squared, we get 2x, and if we integrate sine 2x. So we know that sine integrates to negative cos, but because of the 2x, we have to apply the reverse chain rule. So if you were to differentiate something that was a function of 2x, because of the chain rule, you would be multiplying by 2. For that reason, we're going to divide by 2. So bringing it all together, you're going to get negative a half cos 2x. Now I'm going to call that integral I. And so using the formula, our integral is going to become negative a half x squared cos 2x minus the integral of, so we're going to do a minus a half times the 2 will become minus 1. So we're going to end up with negative x cos 2x. But because we're subtracting the integral, we can actually just double negative, make that a positive, and you're just going to end up with x cos 2x dx is this thing we have to integrate at the end. Now you might think, okay, well, I actually know how to integrate that by parts. So we're just going to do it again. So the spicy element here comes from having to integrate by parts twice. So I'm going to use the same method. So I'm going to imagine we're going to deal separately with the integral of x cos 2x. So if we say that u is x, v dash is cos 2x. U dash will be 1, and v, so let's use the idea reverse chain rule, so we need the half in there, cos integrate to sine, so you're going to get a half sine 2x. So this integral is going to become uv, so you're going to get a half x sine 2x minus the integral of a half sine 2x times 1. So it's going to become a half x sine 2x. Now when you integrate sine, you get minus cos. Because of the 2x, we also need to divide by 2 again. So we're going to end up with positive a quarter cos 2x here. I'm going to put plus c in brackets. So actually, because we're going to be bringing it back in up here, we're going to end up with one constant of integration. So bring it all together. So our integral is going to be minus a half x squared cos 2x. Now ordinarily I would put some brackets in, but because we've only got one of this integral, it's not too important. So we oops. Go on walkabouts. Right, we need some space. Let's rub that out and move a bit over. So our integral is going to become minus a half x squared cos 2x plus a half x sine 2x plus a quarter cos 2x plus c. So that is how we integrate x squared multiplied by sine 2x. So if you get an x squared in there, it means that potentially, probably, if you take that to be your u, you're going to be differentiating it twice. Example 8. So this is our hot pepper, this is our spicy question, and this is a really fun one to finish. So our last question of the video. So we're going to be using integration by parts formula. The integral of uv dash is equal to uv integral of v dash. You've heard that a lot in the last half an hour. Now the question is, what are we going to do here? In the previous examples we were choosing our x, our kind of a linear function, or x squared, or a lot of time we were choosing our natural log of x to be our u. We don't actually have either of those here. You can potentially choose either actually, but what I'm going to do is I'm going to show you how we could do this by taking our sine x to be our u and our e to the power of x to be our v dash. Now you've seen during the video, I've also been quite often labeling the integral I, and that's going to be very helpful to us here. So let's work this through. So if we had u equals sine x, then your u dash would be cos x. If your v dash was e to the power of x, then if we integrate e to the power of x, we get e to the power of x. Now that is one of the nice reasons for choosing e to the power of x to be your v dash, because it's quite an easy thing to integrate. So let's put these into our formula. So the integral is going to become uv, so e to the power of x sine times sine x, minus, subtract the integral of v u dash, so e to the power of x cos x dx. Now this is where you might be going, well I've kind of got myself into another situation. We've got a similar integral. We've actually got the integral of e to the power of x cos x that we've got to do now. So what I'm going to do is I'm going to do the same idea. I'm going to take here my u to be cos x and e to the power of x to be my v dash again, and I'm going to do integration by parts for a second time. So we're going to say u equals cos x v dash equals e to the power of x. Differentiate cos x, you get negative sine x. Integrate e to the power of x, we get e to the power of x. So we set up a second grid, and now we can say that the integral of e to the power of x cos x dx is going to be uv, so we're going to get e to the power of x cos x, subtract the integral, and because it's negative sine x times e to the power of x, I'm going to actually turn this into a positive, so it becomes plus the integral of e to the power of x sine x. I'll run out of room slightly there, so let's just shrink that a little bit. It's tougher to do that on an exam paper, but this is the benefit of using a bit of technology. dx. Now, the reason I shrunk that to fit that in, because that dx on the important is very useful. You know, you can't be leaving that out. I see that often when I'm marking students' work. Okay, so next step is to integrate that last thing. But then you go, well, the issue here is that that's my first question. So we end up going around in circles. So how are we going to get around this? Now the clever thing is what we can do is it's kind of a circular technique in that, well, that is the original integral. And because we called the original integral I, I'm actually just going to call that I. It's nice because it saves a bit of space. So if we put this back in, because remember the reason we're doing this second integral because it fits in here. So our original integral is going to be e to the power of x sine x minus the integral of this, and this is this, so it's going to be minus, put it in brackets, e to the x cos x plus I. So we can actually multiply out our brackets here. So we get the integral is equal to e to the power of x sine x minus e to the power of x cos x minus I. Very nicely now we can actually move our I to the other side. So we're going to get 2I now is equal to that right hand side. Just going to shrink our working a little bit so we can, so in the PDF of the notes will be a bit neater. So if we move that over, so we're now going to have 2I is equal to e to the power of x sine x minus e to the power of x cos x. And we can actually just make I the subject that way. So I love this question because adds a little bit of a different element to your standard question. Actually, we can also factor out e to the power of x, so let's do that as well. So we can take out, so we've got the half, we can actually bring the e to the power of x out. That's a nice, if maybe you're trying to find some, it's just nicer. Right, so that's our spicy question complete. One last thing that might help you with your integration by parts questions, and when you're trying to decide which function to be your u and which one to be your v dash, so the u or the derivative. This is an order of how you should do it. So if your function has a logarithmic function in it, so for example an lnx in it, or even an lnx squared, or maybe lnkx, these sorts of things, this should be what you choose to be your u first. Then if you don't have a natural log in there and you have something like an x or an x squared with maybe a trig function, then that's what you should choose. If you don't, I mean, most A-level questions nearly all have those so it's more, if it's got a natural log, really, that should be your u. But then a trigonometric function, so for sine x, so for example, in that previous example, we took sine x and cos x to be our u when we had an exponential, and the last one is an exponential function. So that's often the last one you choose to be your u. So that might help you in an exam. If you have a natural log in there, that's going to be what you want to choose to be your u because you want to be differentiating that. If you don't, it's probably going to be something like an x. If your function isn't in terms of x, it'll be a theta or a k or whatever you're integrating with respect to. Okay, so to summarize what we've learned in today's integration by parts video. So firstly, we have this lovely formula up top. So that is in the formula book for all of the exam board specs. But I do think it's important that you be confident with that, and maybe you don't even need to look in the formula book to see it. The key thing is splitting up your function, choosing something to be the u and something to be the derivative of v. Once you've done that, you know that you're going to just differentiate this way and then integrate to find out your missing things. If you're ever unsure about what to choose to be your u, this little acronym helps you. And so remember that normally if there's a natural log in there, that's normally what you're going to be choosing to be your u. If not, it's going to be things like x's, x squared, or thetas, or whatever you've got in your function. So I hope you enjoyed today's video. The PDF with all the work solutions from this video can be downloaded from the Hench Maths website, which is down in the bottom left corner there. And to leave you with 3 questions so you can have a bit of practice. So we've got the integral of x squared times the natural log of x, the integral of theta times by cos squared theta d theta, and the spiciest one there is the integral of the natural log of x squared with some limits. So have a go at those, see how you get on, and thank you for watching my video.